Let's talk about electricity, motors, and generators. So motors and generators are transducers. Transducers convert one thing to another. They're transducers between mechanical power and electrical power. So I'm putting mechanical power in. You can see the work I'm pushing on the lever, and I'm getting electrical power out. And I have to push on that. Now what if I don't get any electrical power out? What if I disconnect it? See how easily that turns around? So I don't have to do any work in. Power in equals power out. I don't draw any current. I don't have to push. They're very similar devices. Almost the same. Just how almost? Let's take a look. What if we hook the generator itself to an external voltage source? So the generator was then a motor. So how about if we have two and we hook them together? Now one of them, in my hand, I'm generating electricity with it. It's a generator. What about the other one? Well, so now which one is a generator and which one is the motor? So what is mechanical power and what is electrical power? Electrical power is current times voltage, where current is a flow of electrons and voltage is how hard we're pushing the electrons. Mechanical power is force times speed, or if we're rotating is torque times omega, or the rotation rate. When we turn a generator, the speed of the turning is proportional to voltage. So let's take a look at the relationship between spinning and voltage. Sorry, this is upside down. So I start spinning very slowly. We're at 3 volts. And you can see the faster I spin, 8 volts, 10 volts, I think I get it to 12, 13 volts. So the rate at which you turn the generator is proportional to the voltage you get out on the other side. And you don't have to push at all if there's no current being drawn, which we've seen. Because if you draw no current, there's no electrical power. And if you draw no current, then the handle will rotate freely in your hand. However, if you choose to draw current, the more current you draw, the harder it will be to turn the generator. Voltage is equal to current times resistance. It's kind of like in water, the pressure that you have to drive some water through a sprinkler head or through a hose is equal to how hard it is to push it through the hose times the amount of water or the current of water that you push. Let me give you these analogies a little clearer. Voltage is like the difference in height between a body of water up on a cliff and a body of water at sea level. And so if you were to connect these two by a pipe, you'd have very high pressure here. And so that pressure, you could think of it as how badly the water wants to go downhill. That pressure is like the voltage that corresponds to how badly the current wants to flow from positive to negative. Now, we would never do that because we would lose all our potential energy without getting any work done. So we throw a light bulb in and we force this current through that tiny filament to heat it up into thermal energy, into radiant energy. Just as if we were to not let the water just flow down the hill, but flow through a little turbine that turns that potential energy of the water into kinetic energy. The power that we would get from this circuit is the current times the voltage, how hard we're pushing it. Just like the rate of power would be equal to the flow rate of water through this hose times the pressure, how hard it's pushing. Okay, what happens if you put another light bulb in series where the current has to go through here and through here? That would be similar to stopping the water halfway through and driving your turbine, and then after the water stops, starting it again. And so what you would lose here is, you have 2 light bulbs or 2 wheels, but you would lose the pressure. And so you get less power from each of these. But the same amount of current that flowed through the first device would flow through the second. Now, if you want to get more power, you would just add another wheel down at sea level. And so this wheel here would have the same pressure that it always did, and you just added this one. So you've doubled the amount of power. And you could do the same by running two wires in parallel, it's called, where the electrical current can go through one light bulb or go through the other one independently. So you get twice as much power out. Of course, you see that you have to put twice as much current in as well, so you'd be drawing power from the battery at twice the rate, or power from the reservoir up here at twice the rate. Electromagnets. With a voltage source and a coil, we can get a current through this coil and it generates a magnetic field. We'll try this in activities section. We can get very strong electromagnets in this fashion, and you've probably seen videos of them picking up cars in junkyards with big electromagnets on cranes. And so there's this idea, could we make electric motor like that? So what if we connected this up and we made a north pole here and a south pole here and it aligned? And then we could switch the current and it would make this the south pole and this would want to line up here. And if we kept switching it, we could make this turn around and around and around. And so that's how an electric motor works. Imagine you have a battery right here, and it drives a current through this coil. This coil is magnetized such that it wants to rotate in the counterclockwise direction, there being a force outward on this rung and a force inward on that rung. What will ultimately happen in this will align so that this side of the coil is pointed up. And so what we need to change the direction of current so that once it aligns, this end will become north of this electromagnet and want to align downward. And so we can do this by means of what's called a split ring commutator or a DC commutator. Because we can see right here, this red represents an insulator. So the current has to flow around like this. And we see when it becomes aligned, such that the red line is vertical, it will turn just a little bit further because it has momentum. And this point here will be connected to this side now, and it will change the direction of current. And so it will push itself around one more half rotation, and again it will change direction, and it will continue to go. And that's how an electric motor works. If we go back a century or two, this is what people knew. That with voltage, we could produce current. And we could use an electromagnet, and that current could produce a magnetic field. And we could take that magnetic field with some current, and we could make an electric motor that would give us kinetic energy. And so what we thought is, we wish we could find a way to turn this around and make voltage. Right? We knew how to make voltage already. We could use batteries through chemical processes, but it was very expensive. And so we thought, well, what about if we had motion and magnets? Could this give us voltage? And we could turn kinetic energy into electrical energy, which is the opposite of what a motor does. What happens if instead of driving this around with an electrical voltage source, we instead push it with mechanical energy and put a light bulb here? That change of magnetic flux through the main coil will generate a voltage down where the light bulb is. But because we're driving current, we look at it and we say, this is now the plus side. This is where the current's coming out. So every electrical generator is also a motor. The change in magnetic field produces voltage. The faster you spin, the more voltage you get. If there's no current, then you don't need to put any force on the motor. If current is drawn, the generator itself acts like a motor. So if we let current flow through here, this becomes an electromagnet, and it puts a torque on this, pushing it backwards against us. And so we can see if we allow current to be drawn from our generator, we're going to have to do more work to push it against that magnetic force. And so if we draw electrical work out from our generator, we're going to be forced to put more work in. What if we don't have a DC commutator where the wires change contact every half turn? What if we keep one wire connected all the time? Then as this goes around, it's going to force current back and forth. And so when we look at the voltage on this resistor, on this light bulb or whatever it is, it will be alternating current back and forth, as opposed to DC, direct current that we get from a battery. And so if you were to look at the voltage on a battery, you would see a constant voltage. But if you look at the voltage from an AC generator, which is the same voltage we have in the sockets of our house. It goes positive, negative, back and forth. It changes direction 60 times a second, or we say 60 hertz. So you've probably heard the term 120 volts, 60 hertz. And it sounds about like, that's about 60 hertz. And that's the sound you hear from devices like transformers that draw a lot of current, because that oscillating current causes changing magnetic fields, which put forces on the wire and make them wiggle at about 60 hertz. So you hear, is that sound. If we review what we learned, is a motor is a generator. If you are putting in mechanical energy, you're getting electrical energy out. That's a generator. If you're putting in electrical energy and you get mechanical energy out, then it's a motor. We learned about voltage is very much like a pressure difference from high and low elevation, and current in a wire is very much like current of water in a pipe. And then we learned about how we can create a motor by using an electromagnet, and how if we turn it around, that rotating coil in a generator can be used to generate voltage from mechanical energy.